chemistry, the mole is a fundamental unit that helps us count incredibly tiny particles, like atoms and molecules, in a manageable way. Think of it as similar to how we use the word dozen for 12 items, but on a much grander scale. Because atoms are so small, even a tiny amount of a substance contains billions upon billions of them. The mole allows chemists to express these huge numbers with a single, simple term, making calculations and communication much easier in the lab and classroom. One mole always contains exactly 6.022 times 10 to the 23rd power particles. This massive number is called Avogadro's number. It's a constant that applies whether you're counting atoms, molecules, or formula units. For example, 1 mole of carbon atoms contains 6.022 x 10^23 carbon atoms, and 1 mole of water molecules contains the same number of water molecules. This consistency is what makes the mole such a powerful tool in chemistry. Depending on the substance, the particles in a mole can be atoms, molecules, or formula units. For pure elements like carbon or zinc, we count atoms. For compounds made of nonmetals, such as water or methane, we count molecules. For ionic compounds, like sodium chloride, we count formula units. This distinction is important because it determines how we interpret chemical formulas and perform calculations. Formula mass, also known as molecular mass or molecular weight, is the sum of the atomic masses of all atoms in a molecule or formula unit. It's measured in atomic mass units, or AMU. To calculate it, you look up the atomic mass of each element in the periodic table, multiply by the number of atoms of that element in the formula, and add everything together. This gives you the mass of a single molecule or formula unit. Molar mass is closely related to formula mass, but it's expressed in grams per mole, g/mol. It tells you the mass of 1 mole of a substance. For example, water has a formula mass of 18.02 AMU, so its molar mass is 18.02 grams per mole. This relationship allows chemists to convert between the mass of a substance and the number of moles, which is essential for laboratory work and chemical reactions. Find the molar mass of a compound. Add up the atomic masses of all the atoms in its formula. For example, glucose C6H12O6 contains 6 carbons, 12 hydrogens, and 6 oxygens. Multiply the atomic mass of each element by its number of atoms, then sum the results. For glucose, this totals about 180.16 grams per mole. This process works for any compound, simple or complex. One of the most common tasks in chemistry is converting between grams and moles. To convert grams to moles, divide the mass of your sample by the molar mass of the substance. This tells you how many moles are present in your sample, which is crucial for measuring reactants and products in chemical reactions. To go from moles to grams, simply multiply the number of moles by the molar mass. This conversion is used when you know how many moles you need for a reaction and want to measure out the correct mass. It's a straightforward calculation that's used daily in chemistry labs. If you want to know how many atoms, molecules, or formula units are in a sample, multiply the number of moles by Avogadro's number. This gives you the total number of particles present. It's a powerful way to connect the macroscopic world we can measure to the microscopic world of atoms and molecules. Sometimes you need to convert from grams all the way to atoms or molecules. This requires a 2-step process. First, convert grams to moles using the molar mass, then convert moles to particles using Avogadro's number. This approach is essential for complex chemical calculations and ensures accuracy in your results. Elemental analysis lets you determine how much of a specific element is present in a compound. By looking at the subscripts in the chemical formula, you can calculate the number of moles of each element. For example, in propyl acetate, C5H10O2, each mole contains 5 moles of carbon. If you have 1.5 moles of the compound, you have 7.5 moles of carbon. This method is vital for understanding composition and reactions. Ionic compounds are formed from the attraction between cations, which are positive ions usually made from metals, and anions, which are negative ions usually made from nonmetals. These oppositely charged ions come together to form electrically neutral compounds. Understanding how to write and interpret their formulas is a key skill in chemistry. Writing the formula for an ionic compound involves a 5-step process. First, identify the symbols for the cation and anion. Next, determine their charges based on the periodic table or polyatomic ion table. Then, swap the charges to become the subscripts for the opposite ion using the criss-cross method. Simplify the subscripts to the smallest whole number ratio. And finally, check your work to make sure the total positive and negative charges balance out to 0. Acids are substances that release hydrogen ions in water. You can recognize them because hydrogen is the first element in their formula. There are 2 main types of acids, binary acids and oxyacids. Each type has its own naming rules, which help chemists quickly identify the composition and structure of the acid. Binary acids consist of hydrogen and 1 other nonmetal element. Their names start with the prefix hydro, followed by the root of the nonmetal's name, and end with ic acid. For example, HCl is called hydrochloric acid. This naming convention helps distinguish binary acids from other types of acids. Oxyacids contain hydrogen, oxygen, and a polyatomic ion. Unlike binary acids, they do not use the hydro prefix. The naming depends on the ending of the polyatomic ion. If it ends in ate, the acid ends in ic. If it ends in ite, the acid ends in ose. For example, H2SO4, which contains the sulfate ion, is called sulfuric acid. Some acids, especially those containing phosphorus or sulfur, have slight spelling exceptions in their names. For instance, phosphoric acid is used instead of phosphoric acid. These exceptions are important to remember, as they appear frequently in both academic and professional chemistry settings. Some elements naturally exist as pairs of atoms, called diatomic molecules. The rule of 7 helps you remember them: H2, N2, O2, F2, Cl2, Br2, and I2. These elements are never found as single atoms in nature. Recognizing diatomic elements is crucial for writing correct chemical equations and performing accurate conversions. Knowing whether you're dealing with atoms or molecules is key when performing chemical conversions. For diatomic elements, always use the molecular form in calculations. For other elements or compounds, use the correct terminology to ensure your answers are accurate and meaningful. Dimensional analysis is a mathematical technique used to ensure units cancel out properly in calculations. By aligning units across from each other, you can confidently convert between grams, moles, and particles. This method helps prevent mistakes and guarantees that your final answer is in the correct unit. In chemistry, answers are often written in scientific notation, especially when dealing with very large or very small numbers. Place the decimal after the first non-zero digit and use powers of 10. Also, always match the number of significant figures in your answer to the precision of the data you started with. This ensures your results are both accurate and properly communicated.